One, two, okay, it's working. So I'm going to talk about, this presenter said, the BBC microbit. We are going to see that it is a very interesting device for people interested in analyzing some 2.4 gigahertz protocols. So just first, I'm going to present myself. I'm the head of research and development at Cauquil Digital Security, which is a French company. I'm also a senior security researcher, and I'm a great fan of reverse engineering, both software and hardware. So let's jump into it. We are going to see in the start of this presentation what the BBC microbit is, what its features are, and what we can basically do with this kind of device. And then we are going to hack into this tiny piece of device. We're going to try to turn the microbit into a sniffer and see what we can do with this. I got some nice demos to show you then, and I will also talk about the radiobit firmware I've created to make all of this possible. So the BBC microbit is basically a tiny PCB with some interesting stuff on it. It has a 5x5 LED matrix, so if you want to display some text, make it scrolled, and so on, this is possible with this device. It also has 2 buttons if you want to have some kind of a basic user interaction. It also has a custom expansion connector you can use to plug it into a robot and so on. The people who designed the microbit also designed a lot of kits you can buy on the internet to plug this microbit into. So if you want to make a robot that follows a path, this is possible, and so there are a lot of them. It's also have some kind of wireless capabilities, so you can make 2 microbits communicate over the air. So this part is quite interesting, but the most interesting part in it is that it supports MicroPython. I don't know if you know about MicroPython. So this is basically a Python interpreter embedded into a microcontroller. So this is very cool because instead of developing in C or C++, you can just write some code in Python and make it run on the microcontroller, which is here the microbit. So this is very interesting. One of the other interesting fact is that it only costs 15 euros. You can order it on Keytronic in the UK, for instance. So this is very affordable. If we have a deeper look at the specifications, so it is based on a Nordic semiconductor chip, which is the NRF 51822. Well, this may sound quite weird, but in fact, it's just a 2.4 gigahertz GFSK transceiver. So this is a little tiny chip which has a CPU, some flash. We have a 256 kilobytes of flash, some RAM, and some internal peripherals to be able to modulate and demodulate the radio signals. It's also 3-volt powered, so you can power it with 2 AAA batteries. So this is also a good point for this tiny device. It's also easy to program if you want your kids to be able to program it. There is some Scratch-like Scratch-like service on the internet. You can just put blocks and program it with this service. The microbit guys also provide an online Python editor if you want to jump into the Python code and do whatever you want with this microbit. If you connect to the microbit to your computer with the micro USB port, you can get a console, a serial port. When using Minicom, for instance, you can get a REPL, which is a read, evaluate, print loop. So you can just type Python code and see what happens on the microbit. Very, very useful for debugging purpose. And of course, it's able to communicate over the air with this transceiver. So basically, the guy who made the microbit implemented their own protocol. So this is a very specific protocol they designed. It's not some kind of Bluetooth or other, but in fact, the transceiver itself can handle many protocols, such as what Nordic semiconductor called the shock burst protocol. I don't know if you have ever heard about this protocol. Maybe you're using it during all the week, but you are not, you do not know that this is a protocol you are using. So this is basically used in most of wireless keyboards and mice. You can have at home. So this is a very widespread protocol, and the next version of this protocol is also handled by the microbit, and say the 51822, which is the enhanced version of this, enhanced shock burst protocol, also called ESB. And of course, this is a BLE-enabled chip, which simply means that we can do some Bluetooth low energy stuff with it. In fact, the microbit software comes with a very tiny stack we can use, BLE stack, to create services and create peripheral devices that that will be able to communicate over BLE. So this is quite interesting too. So when I saw this, when I saw all this protocol and all these wireless capabilities, I was like, wow, this is Christmas. Why this is Christmas? Because the enhanced shock burst protocol have been broken by Mark Neolin during DEF CON 24. He managed to hack into various devices such as wireless keyboard and mice. So this is quite interesting. So just to give you some details about this hack. So Mark Neolin used a specific device called the Quasi Radio, which is based on the same, not exactly the same transceiver, but another one. He developed the Mergejack protocol, Mergejack framework, sorry. So this is a framework written in Python you can use to hack into a wireless keyboard and mice, which is open source, available on GitHub. They also created a nice website called the mergejack.com. You can find every vulnerable device on it. So if you are interested in hacking wireless keyboard and mice and go maybe further with this device, you can have a look at it. And also, it's written in Python. But Mark Neolin didn't do the hack itself. The hack itself relies on the hack found by Travis Goodspeed and published on his blog. So this is a hack targeting the NRF 24L01+, which is another transceiver made by Nordic Semiconductor. And this is very interesting because we can turn the microbit into a non-fungible device. Instead of just using to make it blink some layers or communicate with the robots, say, we can do more interesting stuff with it. So let's have a look at what we can do with it and how we can hack into this microbit. So first of all, I will just quickly detail the hack discovered by Travis Goodspeed, which is a very nice hack. How it works. This is a transceiver. We have the NRF 24L01+, which basically takes some signal from the 2.4 gigahertz bandwidth and then demodulates and turn the wireless signal into a bit stream. So this is the interpreted bit stream. Normally, the ESB protocol, so the enhanced shock burst protocol, starts with a preamble of 55 in eggs. So this is a 1, 0, 1, 0, 0, 1, 0, 1, 0, 1, and so on. So it's a very well-known preamble because it's often used to synchronize the decoder with the bit stream. This preamble is followed by an address. An address could be from 3 to 5 bytes long. So this is the protocol that states this, followed by a specific byte, which is used here for the dynamic payload length. So you can send variable length payload over the air with this protocol, followed by the payload, and at the end, 2 bytes CRC. So basically, when you are using this transceiver, you must set an address, and the transceiver matches the address with the payload got from the wireless signal. So you can only listen to a specific address. You cannot sniff, literally. So what Travis Goodspeed discovered is that if we set up a specific register in this transceiver to a specific value, which is undefined normally, this is precise in the datasheet. Normally, it's an invalid value. If we set the address to be only 2 bytes long, we can have a very different behavior from this transceiver. That means we can match the address on the original preamble and get the address field in the payload. That means if you set up your transceiver this way, you can sniff everything because the address will match every payload, every preamble, sorry. So this is quite interesting. The fun fact is that the original preamble is not checked by the transceiver. So this is what we can call a hardware vulnerability of this transceiver, and we can exploit it to turn the transceiver into a sniffer. So this is what Mark Newlin-based Mousejack framework uses to turn his crazy radio into a sniffer and capture every packet sent in the air with the unknown shock burst protocol. So why is it interesting? Because I discovered that the 51822 has exactly the same issue. That means you can turn your microbit into a sniffer using the exact same trick. Well, not exactly the same. The 51822 has also a good some nice features. The hack made by Travis Goodspeed is quite limited because you have only 32 bytes of payload maximum. You cannot get more information from your sniffer. So if you have 32 bytes of payload, you are limited because you must get the CRC and the address in your payload to be able to match, to check if the packet is a good one, is a valid packet for this protocol. So basically, you only got 27 bytes of data, useful data. With the 51822, the maximum payload size is 254 bytes. So we can get much more data and get much more packets. In order for this hack to work, we need to hack a bit around with some kind of C++ code. So what I did is just modifying the radio module implemented by the microbit developers into the MicroPython firmware. So I had to put all of this. Basically, I set an address size of 2. Also the endianness to a big endian. And I used the specific address, which is 0055, to be able to sniff with this transceiver. Then we can get a lot of data, raw data from the signal we get from the air, and check if a packet is valid by checking the CRC. So we can get all the bytes, all the bits, and we try to determine if the packet we got is a valid one. If it's a valid one, then we can process it and get what we want. So since I've implemented all of this in my firmware, so I created a modded firmware from the microbit original firmware to be able to do that. We can do it from some kind of from the radio module in Python. So basically, if you want to implement a quick unknown shock burst protocol sniffer, it's done in a dozen of lines, in less than a dozen of lines. So I tried this one. So basically, we have a while true loop, and we get the packets as they come. Of course, these packets are checked with the CRC, so we get all the valid packets. And if you program your microbit with the firmware I made, and if you're using the correct Python code, you would get data from, say, a wireless mouse. So this is my mouse. I'm moving the mouse around, and you can see all the packets sent by the mouse to the USB dongle I plug into my computer. So this is a Logitech mouse. It's very easy to determine because all the packets start with OOC2. But in fact, I can sniff all of this information. But the interesting thing is that we can also send packets, send information. So this technique is not limited to the Nordic semiconductors unknown shock burst protocol and shock burst protocol. We can do the same with any 2.4 gigahertz based protocol that uses the same data rate and the same modulation. So we have a world of possibilities. When we think about 2.4 gigahertz protocols, we think also about Bluetooth Smart, which is a Bluetooth low energy. This chip can be used to make some kind of Bluetooth low energy communication. So why not use it to hack into this protocol? So it's very, very easy to do it because we have all the stuff we need on this transceiver. Just before going more low level with the Bluetooth protocol, I'm going to recall some facts on this protocol. So when you have a Bluetooth device, this Bluetooth device advertises itself on 3 channels, channel 37, 38, and 39. As you can see, the channels are spread over the boundaries just to avoid interferences. So these packets sent by the device has a specific structure and also what we call an access address. The access address is a 4-byte identifier used at the link layer to identify your connection. And for the advertising channels, this address is known. Remember, we can set an address between 3 and 5 bytes with this transceiver, so it's basically easy to make it listen on this advertising packet. So the only thing we have to do is just to set the address with this value and listen to get the packet back from the transceiver. So by doing this, I was able to create a little sniffer for these advertising packets in BLE using the microbit. So here's an example of what you can get from this MicroPython. So this is the raw version of the advertising packets. But basically, it's very easy to read. We'll take an easy one. So 020106, this is a 1 field specifying the characteristic of this device. And sometimes we get much more information, such as the available services and so on, and even the name of this device. Talking about advertising packets, we can also inject our own packets just to create fake devices. So this one, we create a fake BruCON 09 device. I can just run it. But I could have done a demo here just to see if detected by my computer, but I find it more useful to test PDU parsers. Why PDUs? Because PDU are the format used to send data over the advertising packets. So the data I got previously with the O2, O1, 1A and something, this is in fact PDU data. So I'm building a new packet, a new advertising packet with some random MAC address. And I'm going to tweak a bit with the field, the name field, which is a complete local name field here with the tag 09. And I'm going to tell this packet that the BruCON 09 string is 10 bytes long, which is in fact wrong because the field itself takes only 9 bytes. And we're going to see what happens with some kind of Linux tool. So I'm on my box. I'm using a HCI tool, which is a part of the BlueZ framework. And if you look carefully, well, I said if you look carefully, the BruCON 09 device is detected by this tool. But we also got an extra byte, which is not normal, because normally the HCI tool would have detected this packet as a malformed packet and not taken it into account, but in fact it is. So by having a quick look at the HCI tool code, it's very easy to see that there is a line with some kind of with an issue in it, which is this one. The field length is the size precise in the field structure. So this is the first byte. And if the offset is the position we are in the packet for this given field. So if the field length is greater than the total length of the PDU data, so there's something wrong. But in fact, the size of this data is a size +1, because the byte containing the size is not taken into account in this size. So basically, there may be a way to create some kind of buffer overflow in it, but they took some specific steps, and this is not this is more a bug than a vulnerability. You cannot overflow a buffer with this one. We can also sniff BLE connections, so this is performed the same way. The BLE connections are initiated by a Bluetooth low energy connection packet, which is sent over the air. So this packet also has the same access address. And if we get all this information, we may be able to follow a connection and sniff Bluetooth low energy connection between two devices. So this may be interesting. The CRC unit is used for CRC computation, of course. And there are two other parameters that are very useful. The interval is basically the time spent by the device on each channel. And the hop increment, which is the number of channels to jump when we hop from one channel to another. I didn't record that the Bluetooth Low Energy Protocol is based or is using channel hopping, but this is a fact. We need this information to be able to synchronize with the signal and jump from one channel to another. So this is a sniffer. This is a small code able to sniff a BLE connection request, and we can get some information from it. So we flash the microbit with the correct firmware and Python code, and then we can get the information we are listening on the channel 37, and we get multiple connections from a device to another device with different values. With these values, once we know these values, we can just follow the connection and get all the packets. But Python cannot really sniff on the microbit because of incompatible delays. You know, there is some latency by going from Python to the native code and native code back to Python. So this is not a good way using MicroPython to sniff BLE with the microbit, and even with the 51822 in general. So maybe if you want to do this, it would be better to look at the DAL, which is the microbit device abstraction layer, to do this kind of stuff. Based on this discovery, I made some tools. First tool I created is a mouse-jack-like ESB sniffer. This is a very simple tool allowing anyone to sniff some kind of traffic, ESB traffic, and also supports the legacy shock burst protocol and wall sniffing. So this is all the options you can use to sniff. If you want to sniff some information from, say, wireless keyboard, you program your microbit with my code, and you get all the information from the keyboard. That means if you type with your keyboard, you get all the stuff. From this, you may want to recover the keystrokes sent by the keyboard, if of course, if the keystrokes are not encrypted. We can also do some BLE link layer sniffing. Be careful, it's going to be fast, because I'm going raw data from the link layer of the Bluetooth Low Energy on the specific channel. The channel 2 is corresponds to the channel 37 in BLE, so I can get all the data I want. So this may be interesting if you are looking to sniff raw packets without handling all the protocol, just to get some information from over the air, from existing connection and so on. Based on this sniffer and so on, I developed the wireless keylogger, which is in fact a very tiny embeddable wireless keylogger for keyboards, Microsoft keyboards. So there are a lot of literature on the internet about how to hack into the Microsoft wireless keyboard or to tap the keystrokes sent over the air. So I took a microbit and I put some two AAA batteries, and I made this tiny device I'm going to show you. This sniffer is going to use all the MicroPython features available to store the keystrokes in a very small file system. The microbit firmware provides a way to create files in the flash and to store data in it like if it was a file. So this is me planting my wireless keylogger. So here it is. I put the last AAA battery, power it, conceal it in the meeting room, and then yep. So then someone came to the computer, type in some email and password. So this is the email used was moneyhenry@outlook.com. This is a total mess. Okay, so let's keep it this way. So types in his password and so on. So while he was typing his password, the tiny device, which is a microbit, listens all the keystrokes, stores all the keystrokes in his memory. And then I was able to extract these keystrokes by connecting to the microbit, so and pushing a button. So I developed the firmware to be able to send back all the keystrokes when the specific button is pushed. You can see there is a check on the screen, and I get all the keystrokes and the password used. So this one, so the password used here is Henri Meunier with, I see here some lead speak. So this is quite effective, and all of this, of course, is open source and on the GitHub, as I will told you, as I will describe it later. So this is quite interesting. I can get some sniffing, some wireless sniffing about this Microsoft keyboard. Well, in fact, it has already been done by a Sami Camcar with a piece of device you can plug on in the plug, power plug, and so this is not quite so new. I then make some interesting stuff with the Cheerson CX-10 quadcopters. I don't know if you own one. I got one here just for the demonstration. So this is a very tiny quadcopter, and it also relies on some kind of 2.4 gigahertz protocol. So this Cheerson CX-10 quadcopter has been targeted by two well-known person. The first one was Mark Newlin, so the author of MouseJack. And the second one was Michael Osman, the guy who created the HackerF SDR. So at ToorCamp 2016, they battled with some quadcopters just to see if they could take over the each other's quadcopter by abusing this protocol. So the result was not so great. They ended in a draw, so no winner. They make some kind of exploits, and it didn't work so well. So challenge accepted. The idea was to then trying to do better than these guys to take over this quadcopter. So let's have a look at the protocol between the quadcopter remote and the quadcopter itself. So it's very simple. Once you power on the quadcopter, you have to power on the remote. And there is a binding, so you push the throttle stick back and forth. And then this remote control sends some kind of binding request to the quadcopter, which answers back with a binding reply. The binding request contains what they call the transmitter ID, which is a 4 bytes ID used by the remote. And the quadcopter sends back is vehicle ID, which is another 4 bytes value. Then there is a confirmation, and once the binding is done, then you can use your remote controller to control the drone, and the remote controller performs some kind of channel hopping over 4 channels with all the information sent on each channel. So there is a wait time between the two channels, which is of 6 milliseconds. And each time the remote controller jumps on a new channel, it sends some information with all the stick positions and also the transmitter ID and vehicle ID. So you need to know these values if you want to take over the quadcopter. And the idea is to hijack this connection. We are going to try to send quicker the information, the packet, just to take control of the drone. So there is some kind of channel hopping, as I said. But in fact, the channel hopping is not so good because it's derived from the transmitter ID. So the 2 first bytes of the transmitter ID are used to determine the 4 channels used by this connection. So let's hijack. The process is pretty simple. We need to sniff a valid packet from channels 3 to 18. So the first group, the first possible channels for the first channel used in the channel hopping mechanism. Once the valid packet is found, we got the transmitter ID and vehicle ID. Then we checked the current channel based on the transmitter ID, we derive exactly the same way the channels and see if the channel we are listening on are in this list. And then when we get the confirmation that we get the correct transmitter ID and vehicle ID, then we synchronize and we send packets quicker than the original remote just to take control of it. So the problem is that this quadcopter doesn't use a Nordic semiconductor transceiver. It uses some Chinese one, which is not so standard. So I got to tweak my microbit a bit just to be able to be compatible with this transceiver. This transceiver uses a custom preamble which is not 55 but 71OF55. But doesn't matter if I put this preamble in the address field, it would match with the Nordic semiconductor 51822, and I would be able to send and receive to this address with this custom preamble. And of course, I can use this preamble to hijack the whole protocol. So we can blah blah. End of the day. So we are setting up the radio with some Python. So we enable the CX mode just to be able to communicate with the transceiver used by the quadcopter and the remote control. We find a valid packet by sniffing for some valid packet sent by this transceiver, and we check if the transmitter ID is the one expected by deriving over all the channel and checking if the channel we are listening on is in this list. And once we get the vehicle ID and transmitter ID, we just synchronize by listening on the first channel and waiting for a packet to be sniffed. And once we got a valid packet, we just jump from one channel to another at with a 6 millisecond delay between each channel. And once we have done all of this, we can just send valid packets and try to control the quadcopter and take it over, take control of this quadcopter. So this is possible to send packets with a microbit, but in fact, we also need a controller to be able to pilot the quadcopter. It's very easy to make with a microbit, but the microbit doesn't have all the stuff we need to fly this quadcopter. So I thought about using a classic remote controller used in IO modeling. So this is the DX6 of Spectrum. Maybe some of you knows about this kind of controller, but in fact it's not so easy to interface with the microbit. So this was not a good choice. I thought about using a USB compatible gamepad, which is in fact the same kind of remote, but with a USB interface. The fact is, if I use this kind of controller, I need to plug it on plug this controller into a computer, and then the computer to the microbit, and the computer has to do the relay, the interface between the microbit and the remote, and it also introduces some delays due to the serial port. So this was not a good choice. So I needed to find another controller. So well, I was a bit desperate. Thought about using a foot gamepad, but no foot at home and not enough buttons. So I had to find another type of controller. Well, why not? We're using a CX10 remote controller. We have all the sticks in it, and we got all the stuff we need to fly the drone. So let's go. We took we had to put some wires between the sticks and the microbit using the expansion connector, and then we are able to make some kind of pseudo expansion connector for us in order to plug our microbit in it. Of course, I removed the original transceiver from this remote just to be able to drive it with the microbit. So with this remote controller, we can easily read the sticks value, which is basically some potentiometers. You're using the microbit firmware, the original firmware, so with the read analog method. And then I implemented all of this. I managed to get to take control of this quadcopter. So I'm going to to show you a small video with the test bed. So this is this exploit. So I powered on the quadcopter. I bind it with a remote controller, so I can fly it. Well, fly. I keep it on the table just to be sure that there is no problem. I plug it my Rogue remote controller. So if I take the original controller back, nothing happens. But if I take my Rogue controller, then I got full control on the quadcopter. So I hijacked the quadcopter in flight, and this attack works. So going to try a live demo of this hack. I got my personal pilot right here. Well, expect some misbehaviors. So I got the microbit. So this is the one where I put some kind of connectors on it, and I plug it into my Rogue controller. So this is I don't know for those who are far away if you can see this, but it will be available right after the talk. And I also got this Cherson quadcopter. So I will ask Xavier to fly the drone. Be careful, this yeah. So I think you can land it onto the table if you're skilled enough. I'm going to perform the takeover while the quadcopter is on the table to avoid yeah, that's it. To avoid issues. So I'm plugging my fake remote. Just, yeah, try okay, so I got control. So this time, this is me. Xavier, can you show people that you are unable to fly the drone? So I'm going to try to land it nicely in the table. Well, not in the table, on the table. That's a bit weird. Well, my skills are not so good. Yeah. We're going to make just a little test. Try to fly it again. OK, so the original remote is disconnected. So I totally hijacked your quadcopter. So it worked. Well, good. I also plan to show you a video if this failed. So as a result, sometimes the remote controller gets disconnected. This was the case here during the demo. So maybe due to a timing issue. This hack is totally open source. I put all the code on the GitHub, so feel free to hijack some drones. But be careful too, because you can hurt people. So, and of course, hack only your quadcopters, not others. It doesn't work for the green version. If the Cherson is green, there is a slight difference between the two, mostly on the stick values used by the remote controller. So if you are using this hack, it will work. You will manage to take control of this drone, but if you try to fly it with a Rogue controller, it's a total mess. You are not going to make it go wherever you like, and well, it doesn't work pretty well with this version of this controller. So all of this stuff is open source. So I designed the what I call the Word-a-bit firmware. So this is a modded version of the original microbit firmware, which is in fact also a fork of MicroPython. So you can get it on GitHub. I included all the tools, so you can easily intercept ESB protocol, the Unknown Shockburst protocol, the Shockburst legacy protocol, the Cherson CX10 protocol if you want to play with it. And also a very small stuff related to the Bluetooth Low Energy Protocol, because I'm currently working on it. It's not completely yet, but everything I presented in this presentation about the Bluetooth Low Energy Protocol is presented in this framework. So if you want to get it, there is an URL, a quick link on GitHub. You can get it. I pushed some modifications, I guess, or we pushed some modifications on this one of the tools. But in fact, we can already get it and sniff all of this. As I said, you can also inject. So if you want to play with some 2.4 gigahertz protocol, you can do it. So since it's very easy to use, well, I'm expecting some kids to have fun with it, and maybe it would be interesting. You know, I gave a slightly different version of this talk at DEF CON this year, and a mom came to me right after my talk, asking me about, you know, I get a smart kid at home, and I don't want him to hijack all my wireless keyboards. So, what can I do to avoid this? Do you have some advice? No, but maybe change your keyboard. I don't know. Or use a wired keyboard. I don't know, but in fact, if you want to put a few bucks, like 15 euros in this microbit, you can buy it very easily. This is, in fact, a cheap, tiny, and battery-powered radio frequency hacking tool. So you can just use the modified firmware I made to play around. It allows also rapid prototyping with ESB, SB, so the Nordic protocol, and also Bluetooth Low Energy Protocol. So it's quite better than the MOSJack framework by Bastille, because it doesn't get a limitation of the 32 bytes of payload you can sniff. And we can do even better with the microbits, the device abstraction layer, which is written in C++, and also open source. So if you want to go deeper with the microbit in this implementation, you can do a lot more with the device abstraction layer. So the future work with this device is to try to implement an open source BLE sniffer, like the one provided by Nordic. I don't know if you followed the workshop yesterday afternoon, which was about hacking BLE smart locks. But in fact, Nordic Semiconductors developed a closed source sniffer, a specific firmware you can put on your 51822 just to be able to sniff Bluetooth low energy devices. But it's quite buggy, and it sometimes works, sometimes not. So I'm trying to make an open source version of it just to fix all of this. We can also add support for other 2.4 gigahertz protocols. I put the XN297 transceiver support into the firmware, but we can do the same with a lot more protocol. And I plan to make some keyboard and mouse injection tool with some kind of nice payload just to hijack, say, Logitech keyboards and mouse. And the same with the Microsoft keyboard. In this presentation, I showed that it was possible to sniff keystrokes, but in fact, you can also inject keystrokes. This is more interesting because if you can do the same like a rubber ducky, for instance, or a Teensy with this microbit, it could be wonderful. And as a bonus, I will show you where the current work I'm working on with the microbit. So this is some kind of BLE related stuff. I'm using the device abstraction layer to try to sniff Bluetooth low energy communications and connections. So just to explain what happens here, I got on your right. Oh, goes so fast. On your right, the mobile application. This is the NRF Connect application. I connected my smartphone to a device, and this one is on my computer. I'm trying to sniff an active Bluetooth low energy connection between my device and my smartphone, based on the microbit. So what I'm going to show you is the actual piece of code I got that performs this Bluetooth low energy sniffing. It's not public yet. I'm planning to release it maybe in 2018. Maybe at a conference or not, I don't know. But in fact, I managed to do the same like the Ubuntu's BTLE tool, which is a SDR-based BLE sniffer that costs around 150 euros, I guess. So I'm doing quite the same with a 15 euros device. So this is pretty interesting. So here it goes. Still buggy. Not time for the question yet. So here it is. I have an active connection between my smartphone and the device. I'm launching some kind of wireless sniffer I designed. So this is a tool that we, this displays not nicely, but that will show the access addresses sniffed over the different channels. So this one is the one created by my smartphone because it has a power of minus 44 dBm. Well, still in development, like I said. And I'm using a small Python code to communicate with the microbit and get all the information back from this connection. So I had to provide some parameters, specific parameters to this tool. This one is the access address. The other one is a channel map used by my smartphone. I will give more details maybe in the next year. And then I recover each connection parameter I talked about earlier, but there was a CRC init value. We can recover like this. So it takes some time to get the other parameters because we have to jump from one channel to another in order to recover the hop interval, which is a time spent on each channel before hopping. And then we got the increment, and I then read some characteristic here and put some value in it, and I get all the link layer data for this connection. So this tool is actually able to export all of this into a PCAP format, file format. You can then analyze it with Wireshark. Well, this is still a work in progress. I got a lot of debug to do before releasing this tool. But here it is. It's possible with this microbit to sniff an active BLE connection with just a small 15 euros device. So this is interesting, I guess. So this is the end of my presentation. If you got any question, if you want to see the setup I've created to hijack the quadcopter, just come to the stage and I will show you. I don't know if there is any question here.